first lesson of Chapter 2, which is about inductive reasoning. The next video you're going to watch is about the second lesson on conditional statements, lesson 2.2. The assignment that you'll do will combine these two lessons. So for today, we are going to describe patterns and use inductive reasoning to make predictions. Tomorrow, you're going to write definitions as conditional statements to verify statements. So this chapter, the beginning of this chapter is all about introducing you to logic. When I was in college, I actually took a college course on formal logic, which has a lot of these different terms and concepts. So you might see this again when you take college class, but the reasoning process can be applied to any subject that you take, such as especially any science class or even language arts classes. So this lesson can be applied to many different subjects in many different contexts. And we'll be using it in geometry as we explore proof writing and proving different geometric statements. So let's first talk about a few definitions. The first one is a conjecture. You might have heard this term before. It just means an unproven statement that is just based on observations. So think about any time where you make an observation about something and the observation that you make hasn't really been proven true. You're just stating it based on what you've seen. So, for example, the bell rings at 7:50 on Monday through Thursday. So a conjecture that you can make would be that the bell is going to ring on Friday. Bell will ring at 7:50 on Friday. Let's say this is the first week of school. You found that the bell rings at 7:50 Monday through Thursday. So you're going to assume, even though it hasn't actually happened yet, so you haven't proved that it's actually true, that the bell will ring at 7:50 on Friday. You could ask your teacher to prove that it's true, but if you're just making an observation, you're going to assume that the bell will ring on 7:50 on Friday. Okay, there's many other good examples you can think of this. For example, let's say your mom makes pasta on Monday, Tuesday, and Wednesday, or maybe you have leftovers on Monday, Tuesday, and Wednesday. You could assume, or you can make a conjecture that you'll have pasta or leftovers also on Thursday. Inductive reasoning which is what this lesson is all about, is the process of finding a pattern. So all about a pattern. So we notice a pattern Monday through Thursday when the bell rings for specific cases and writing a conjecture for the general case. You could also say that the bell will ring every day at 7:50. So that would be the general case. So here's an example, a mathematical sequence. So what would be the next pattern in the sequence of -7, 21, -63, 189? Well, you can see each time you're multiplying by -3. So I'm going to do a little calculation here. 189 times -3 is -567. So we're noticing a pattern, and we make a conjecture about the next number in the sequence, and we could also make a conjecture for the general case by describing the pattern. We could say that you're multiplying by -3. A counterexample is a specific example for which the conjecture is false. So counter means opposite. So basically, it's an example that proves that something is false. So I'm going to make a conjecture that the value, based on observations that I've made, the value of x squared is always greater. Actually, sorry if you already have written this down. I'm just going to make it simpler by just doing an inequality. So let's say that x squared is always greater than the value of x. Because let's say x is 2, then x squared is 4. If x is 3, then x squared would be 9. So what would be a counterexample to this? Well, you can think of several. What about 0? If x is 0, then x squared is 0. That's not greater than, that's equal to. So 0 or 1 or anything between 0 and 1. So actually, for any value of x that's between 0 and 1, this is supposed to be an x, such as 1/2, 1/4, because when you square 1/2, you actually get 1/4. And when you square 1/4, you get 1/16. And in those two cases, the value of x squared is actually smaller than the value of x. So anytime you have a fraction that's less than 1, then this wouldn't be true. So these would all be examples of a counterexample. So as long as you can find just one counterexample, then you know that this is false. So you only need to find one counterexample. One counterexample to prove a statement false. All right, let's look at some other examples about patterns. So describe how to sketch the fourth figure in the pattern. So here we've got kind of the same general outline of a rectangle. This one is split in half with only this piece shaded. This one is split in half again this way. And then only this bottom corner is shaded. So here we have 2 parts. Here we have 4 parts. Here we have 6 parts. So in figure 4, guess how many parts we're going to have? This would be 8 parts. So notice that each of these has 2 rows. And then each time you just add a column. So plus 1 column. So here we just have 1 column, 2 columns, 3 columns in figure 3. So in 4 columns, we're going to have, so in figure 4, we're going to have 4 columns. So I'll try to make the same rectangle with 2 rows, 4 columns, and then the bottom left box will be shaded. All right, number 2. Describe the pattern with these numbers. Write the next 3 numbers in the pattern. So -1, -4, -16, -64. So you can probably see pretty quickly each time we're multiplying by +4. Multiply by 4 each time. So then the next numbers will be -64 times 4 is -256 times 4 again. Actually, yes, we're multiplying by 4 each time. Is -1024 I almost got tripped up. It almost looked like we were squaring, because 4 squared is 16, but 1 squared is not 4, so you're multiplying by 4, not squaring. Negative 4,096. Next example. Given 5 non-collinear points, make a conjecture about the number of different ways to connect the points. So let's say you have 1 point. How many different ways are there to connect the points? Well, if there's only 1 point, then there are 0 ways to connect the points. Let's look at the fifth. Let's look at if there are 5 points, because they give us this example. So how many different ways are there to connect the points? Well, there's 1, 2, 3, 4, 5, and then 6, 7, 8, 9. I feel like I'm missing one of them. Let me try this again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I'll erase this so that you can see everything better. So here, if there are 5 points, then there are 10 different ways to connect the points. Let's go back to 2. Let's say we have 2 points. How many different ways are there to connect the points? Well, there's just, I maybe should use a straight edge. So there's just one way to connect the points. If you want to be able to draw a segment, what if there are 3 points? Non-collinear points, that is. So if there are 3 points, let's see. We have 1, 2, 3, and you can't really go diagonal like you can here. So the diagonals are the same thing as like the outline here. So this is just 3. And then how about with 4? 1, 2, 3, 4. So 1, 2, let's do the outline, 3, 4, and then let's try the diagonals, 5, and 6. So what would be the pattern? Well, notice from 0 to 1, you're adding 1. From 1 to 3, you're adding 2. From 3 to 6, you're adding 3. And from 6 to 10, you're adding 4. So it says the number of different ways to connect the points. So basically, each time you add a point, you're adding an additional way that you can connect the points. So for each point, you're adding an additional way to connect the points. Example 4. Numbers such as 1, 3, and 5 are called consecutive odd numbers. Okay, because they're right. Consecutive means that they come right after the other, and they are odd. Make a test and conjecture about the sum of the 3 consecutive odd numbers. So step 1 is to find a pattern using groups of small numbers. Okay, so let's try the first 3 numbers. So it says about the sum. So 1 plus 3 plus 5 is 9. Okay, let's maybe start with 3. And then it says we're doing 3 consecutive odd numbers. So just 3 numbers. We'll start with 3, so we'll do 3 plus 5 plus 7 would give us 15. How about let's start with 5. 5 plus 7 plus 9 is 21. Okay, so our first step is to figure out a pattern by choosing different combinations of consecutive odd numbers.
Excuse the interruption. Please check your emails from an email from George Woods. We're having attendance questions for our remote learners issues, and it needs to be replaced. The instructions are on the email from George Woods. Please spread the word to any teacher who hasn't arrived yet also. It's real important to get it done as soon as possible for those kiddos who are already logging in. Thank you.
Okay, sorry about that. Anyways, so let's make a conjecture based on our observations. So there are lots of different things you could say here, but one thing that's for sure that you can say is that the sum of 3 consecutive odd numbers is also odd. So the sum of 3 consecutive odd numbers is also odd. And think, if you add the sum of 3 consecutive even numbers, the sum would also be even. And then test your conjecture. So here's how we test in conjecture. So we're going to let our first odd number represent, we're going to go back. Let's say that n is an even number. So if we wanted an odd number, we would have to add 1 to it. So the first odd number is going to be n plus 1. And then the second odd number would be n plus 3, because n plus 2 would give us another even number. And then our third consecutive odd number, can you guess, would be n plus 5. So let's combine like terms. We have 3 n's. 1 plus 3 is 4, plus 5 is 9. So if you take 3 times an even number, you are going to get an even number. But if you add another odd number to it, you're going to get an odd number. So this is how you would test a conjecture with a general case using a variable to represent any even number. So we found out that any 3 consecutive odd numbers also yield an odd number. Okay, and then the last one here. The student makes the following conjecture about the difference between 2 numbers. Find a counterexample to disprove the student's conjecture. So they say that the difference of any 2 numbers, so difference, subtracting is always smaller than the larger number. So they're talking about any 2 numbers. The difference is always smaller than the larger number. So I think what they're saying, for example, is like 10 minus 7 equals 3. So the difference of 3 is always smaller than the larger number. If we did 10 minus 3, we would get 7. 7 is smaller than 10. 3 is smaller also than 10. So can you think of a counterexample to this? Well, what if the number that we were subtracting was a negative number? So, for example, 10 minus negative 7, or 10 minus negative 3. Well, minus and negative becomes plus. So this would actually be 17 and 13, which 17 and 13 are both greater than 10. So a counterexample, you just have to give one counterexample to prove that this statement is false. But the general idea here is that if the number that you're subtracting is a negative number, then that's going to yield if you take a positive number minus a negative number, then you're actually going to get a larger number than the original. All right, that is all for today. The next video that you watch will be on 2.2 conditional statements. Lots more vocabulary.